The universe is expanding faster than the laws of physics allow. Two of the most powerful telescopes ever built just confirmed it. We believed space stretched at a steady, predictable rate. We were wrong. The measurements refused to match. Something invisible is tearing reality apart at different speeds depending on where you look. Webb just revealed galaxies that formed when the cosmos was 500 million years old. They contain billions of stars. That should be impossible. The universe had not existed long enough. If you enjoy unraveling mysteries that challenge everything we know, hit that like button and subscribe. We are about to journey through discoveries that broke cosmology. Prepare yourselves. We begin. Two telescopes pointed at the same universe see two different realities. The James Webb Space Telescope and Hubble Space Telescope just completed the largest measurement campaign in astronomical history. They aimed at distant galaxies, tracked pulsating stars called Cepheid variables, and calculated how fast space itself expands. Both telescopes returned identical measurements. The instruments work perfectly. The data matches. Yet these numbers create an impossible problem that threatens to dismantle our entire understanding of cosmology. Here is what happened. Scientists use Cepheid variables as cosmic rulers because these stars pulse with mathematical precision. Their brightness follows a strict pattern tied directly to their true luminosity. By measuring how bright they appear versus how bright they actually are, astronomers calculate exact distances across billions of light years. Webb and Hubble observed the same Cepheids in galaxies scattered throughout space. The distances matched flawlessly between both telescopes. Then came the expansion rate calculation. When you know how far away galaxies sit and measure how quickly they move away from us through redshift, you determine the universe's expansion speed. This number is called the Hubble constant. Every calculation from both telescopes converged on the same value, 74 kilometers per second per megaparsec. That means, for every 3.26 million light-years of distance, space expands by 74 kilometers per second. The problem strikes when you check this against predictions. The cosmic microwave background radiation preserves a snapshot of the infant universe just 380,000 years after the Big Bang. This ancient light contains patterns, tiny temperature fluctuations that tell us the universe's initial conditions with stunning precision. Scientists use these patterns to predict how fast the universe should expand today. The prediction comes out to 67 kilometers per second per megaparsec, 74 versus 67. The gap seems small. It represents a catastrophe. Nobel laureate Adam Rees led the Webb observations. He confirmed measurement errors were eliminated. The telescopes see reality correctly. That leaves only one conclusion. Our understanding of the universe contains fundamental holes. This is not about instruments needing calibration or data requiring better analysis. Two independent methods for measuring the same phenomenon produce answers that differ by roughly 10%. In cosmology, that gap might as well be infinite. Either the early universe data misleads us about initial conditions, or unknown physics operates between then and now. Something hides in the 13.8 billion years, separating the cosmic microwave background from today. Some scientists call it the Hubble tension. Others prefer crisis. David Gross, another Nobel Prize winner in physics, stated at a conference that this transcends mere tension. The word he used was crisis. The standard model of cosmology rests on the assumption that we understand how the universe expands. If expansion rates contradict themselves depending on measurement method, then everything built on that foundation crumbles. Einstein's equations should govern cosmic expansion. They do govern it, at least partially. But the equations cannot explain why present-day measurements exceed predictions from the early universe. The physics works in both eras independently. Connect them across time and the mathematics shatters. Here is what makes this discovery different from past anomalies. Previous cosmic mysteries involved single observations or isolated phenomena. This involves the most fundamental measurement in cosmology, verified by the two most advanced telescopes humans ever launched. The data passed every verification test. Hundreds of scientists across institutions checked the work. The impossible numbers remain. The universe expands at speeds that should not exist according to our best theories. Webb just proved Hubble was right all along about the measurements. That makes the crisis real. The question now becomes why? What force drives expansion faster than physics allows? The number 67.4 haunts cosmology laboratories worldwide. This value represents how many kilometers per second space expands for every megaparsec of distance based on early universe predictions. The Planck satellite measured the cosmic microwave background with unprecedented accuracy. It detected temperature variations across the entire sky down to 1 part in 100,000. These tiny fluctuations encode the universe's density, composition, and expansion rate during its infancy. Feed this data into Einstein's equations, and out comes 67.4. Meanwhile, every direct measurement of the present universe yields 73 to 74. The discrepancy persists across different measurement techniques and multiple independent teams. Some researchers hoped Hubble's instruments introduced subtle errors that accumulated across billions of light-years. Webb's confirmation destroyed that hope. The measurement error hypothesis is dead. What could cause this tension? One possibility is dark energy behaving differently than assumed. Dark energy makes up 68% of the universe's total energy content. It pushes space apart against gravity's inward pull. We discovered dark energy accelerates cosmic expansion in 1998. That discovery won the Nobel Prize. Yet we barely understand what dark energy actually is or how it operates. If dark energy's strength changed over cosmic history, expansion rates would mismatch between past and present. Another explanation involves early dark energy. Standard cosmology assumes dark energy remained dormant until recently in cosmic history, only beginning to dominate expansion a few billion years ago. What if dark energy activated much earlier? An unexpected energy injection right after the Big Bang would alter the universe's initial expansion speed. That would throw off predictions based on cosmic microwave background data. The early universe would have expanded differently than we calculated. Then there are exotic particle theories. Some physicists propose unknown particles called unparticles that might influence cosmic expansion in ways regular matter cannot. These hypothetical entities would exist outside our standard physics framework. They could push space apart through mechanisms we have not discovered yet. Finding evidence for unparticles would revolutionize physics beyond just cosmology. Changing fundamental constants presents another radical option. What if the masses of electrons shifted over cosmic time? What if gravity's strength was different billions of years ago? The laws of physics might not be as constant as assumed. Measurements across different cosmic epochs would naturally disagree if physical constants evolve. Primordial magnetic fields offer yet another avenue. These would be magnetic fields generated during the Big Bang itself, permeating all space. Their pressure could affect expansion rates in ways current models ignore. Detecting primordial magnetism remains extraordinarily difficult because any signal would be incredibly weak. Every explanation requires new physics. That is what makes the Hubble tension so profound. Something major is missing from our understanding. The standard lambda CDM model of cosmology succeeds at explaining countless observations. It describes how structure formed in the universe. It predicts the abundance of light elements created after the Big Bang. It accounts for galaxy clustering patterns across billions of light years. Yet it cannot reconcile these two expansion measurements. Adam Rees stated that, with measurement errors eliminated, what remains is the exciting possibility we misunderstood the universe. Exciting is one word for it. Terrifying might be another. Cosmology built itself on certain assumptions about cosmic expansion. Those assumptions now stand on shaky ground. The Hubble tension is not going away. Each new measurement confirms it. Webb's data makes it more certain, more undeniable. Somewhere between the cosmic microwave background era and today, something happened that our physics cannot explain. The universe hides secrets in its expansion history. Those secrets might involve how galaxies formed impossibly early. Light from 380,000 years after the Big Bang fills the entire sky right now. This radiation is the cosmic microwave background. Before this moment, the universe was too hot for light to travel freely. Free electrons scattered photons constantly, creating an opaque fog. Then the temperature dropped below 3,000 degrees. Electrons combined with protons to form hydrogen atoms. Light could suddenly stream through space unimpeded. That first free light has traveled for 13.8 billion years to reach us. The Planck satellite mapped this ancient radiation across the whole sky. Temperature differences appear as tiny ripples, typically varying by only a few hundred thousandths of a degree. These ripples are not random. They trace density variations in the newborn universe. Denser regions were slightly hotter, less dense regions were slightly cooler. Gravity amplified these density differences over billions of years, eventually forming galaxy clusters and cosmic voids. Scientists extract extraordinary information from these patterns. The ripple sizes reveal the universe's geometry. Space could curve like a sphere, bend like a saddle, or stretch flat like a table. Measurements show flatness within measurement precision. The ripple amplitudes determine how much ordinary matter versus dark matter exists. Regular atoms make up less than 5% of total mass. Dark matter dominates with about 27%. Dark energy fills the remaining 68%. The cosmic microwave background also constrains expansion rates. The ripples formed because sound waves traveled through the hot plasma before atoms formed. These acoustic oscillations created a characteristic pattern of peak and valley separations. The pattern depends on how fast the universe expanded during that era. Measure the pattern precisely enough, and you determine the expansion rate then and extrapolate to today. That extrapolation assumes standard physics operates unchanged across cosmic time. Gravity follows Einstein's equations. Dark energy maintains constant strength. Particle masses remain fixed. Under these assumptions, the predicted present-day expansion rate is 67.4 kilometers per second per megaparsec. The cosmic microwave background measurements achieve incredible precision, far better than 1% uncertainty. Yet direct measurements of today's universe consistently exceed this prediction. The discrepancy cannot be experimental error. Both measurement methods work correctly in isolation. The problem arises when connecting them across time. Something changed between the cosmic microwave background era and now. One interpretation suggests new physics activated after the cosmic microwave background formed. Maybe an unknown field turned on, injecting energy into space and accelerating expansion beyond predictions. Maybe dark energy's strength increased over time rather than staying constant. Maybe fundamental forces weakened or strengthened as the universe aged. Another interpretation questions whether the cosmic microwave background patterns mean what we think. Perhaps our theoretical understanding of that early epoch contains subtle errors. The sound wave calculations might miss important effects that alter predicted ripple patterns. If we misinterpret the cosmic microwave background data, our predictions for today's expansion rate would be wrong. Temperature maps of the cosmic microwave background show anomalies that standard cosmology struggles to explain. One hemisphere of the sky appears slightly warmer than the other. A particularly cold spot exists that seems too large to form by random chance. These quirks might hint at physics beyond standard models. The cosmic microwave background represents our deepest view into cosmic history. It shows the universe before stars existed, before galaxies formed, before any complex structure emerged. Just hydrogen, helium, lithium, and radiation spread almost uniformly through expanding space. Almost, but not quite. Those tiny irregularities seeded everything that came after. If we misunderstand this early universe snapshot, our entire cosmic timeline becomes questionable. How galaxies formed, when stars ignited, where dark matter concentrates, all depend on accurate cosmic microwave background interpretation. What Webb found in the early universe makes that interpretation even more uncertain. Henrietta Leavitt discovered the cosmic distance ladder in 1912 while studying stars in the Magellanic Clouds. She noticed certain stars pulsated in brightness with perfect regularity. These Cepheid variables expand and contract like beating hearts. Their pulse periods range from days to months depending on their true luminosity. Brighter Cepheids pulse more slowly, dimmer ones pulse faster. The relationship follows strict mathematical rules. This creates a powerful measurement tool. Observe a Cepheid's pulse period and you immediately know its absolute brightness. Compare that to how bright it appears from Earth, and the distance calculation becomes straightforward. Light dims with distance following an inverse square law. Double the distance and brightness drops to 1/4. This relationship never changes. Hubble used Cepheids to revolutionize astronomy. He found them in the Andromeda Galaxy and proved it lay far beyond the Milky Way. The universe suddenly contained countless galaxies instead of one. Now, the James Webb Telescope uses Cepheids the same way, but across far greater distances. Webb's infrared vision penetrates cosmic dust that blocks visible light. It detects Cepheids in galaxies billions of light-years away. The latest measurements tracked Cepheids in galaxies hosting Type Ia supernovae. These stellar explosions provide another distance measurement method because they reach predictable peak brightness. Using both Cepheids and supernovae creates cross-checks that verify accuracy. Webb observed over 1,000 Cepheids across dozens of galaxies. The data quality exceeded anything Hubble achieved. Every Cepheid measurement confirmed the same expansion rate, 74 kilometers per second per megaparsec. The numbers showed remarkable consistency. Different galaxies at different distances all pointed to the same conclusion. The present universe expands faster than the early universe predicts. Cepheids work as cosmic rulers because their pulsations arise from fundamental physics. The stars exist in an unstable equilibrium. Gravity compresses their outer layers, heating them until radiation pressure pushes back. The layers expand, cool, become transparent to radiation, and collapse again under gravity. This cycle repeats endlessly with clockwork precision. The pulsation period depends on the star's mass, radius, and luminosity through equations we understand thoroughly. We can calculate Cepheid properties from first principles using stellar physics. When observations match predictions this precisely, confidence in the measurement technique grows strong. Cepheids have been tested across our galaxy and nearby galaxies where other distance methods provide verification. Some researchers wondered if Cepheids behaved differently in the early universe. Maybe younger galaxies contain Cepheids with unusual chemical compositions that alter their pulse relationships. Webb investigated this carefully. It compared Cepheid properties in nearby galaxies to those in distant galaxies formed billions of years ago. No significant differences appeared. Cepheids pulsed the same way across cosmic time. The precision of Webb's Cepheid measurements eliminates most potential error sources. Telescope resolution matters because galaxies contain billions of stars crowded together. Hubble sometimes blended Cepheid light with nearby stars, introducing small errors. Webb's sharper vision separates individual stars cleanly. Each Cepheid appears distinct from its neighbors. Infrared observations also help because interstellar dust absorbs blue light more than red light. Dust makes stars appear dimmer and redder than they truly are. Measuring stars at infrared wavelengths reduces dust interference dramatically. Webb sees through dust clouds that would hide Cepheids from visible light telescopes. The Cepheid measurements leave no room for doubt. The 74 km per second per megaparsec expansion rate is real. The universe expands at this speed right now, today, in our cosmic neighborhood. That number contradicts predictions based on the early universe by a margin far exceeding measurement uncertainty. Something happened between then and now that standard cosmology does not account for. The cosmic distance ladder, built on Cepheid variables, has been climbed successfully. The view from the top reveals a universe behaving unexpectedly. That unexpected behavior shows up even more dramatically in galaxies that should not exist. 7 km per second separates our cosmology from crisis. That difference sounds tiny against cosmic scales. A human walks faster than 7 km per second sounds when you hear it. Yet this gap represents roughly 10% disagreement between two fundamental measurements of the universe. In physics, 10% discrepancies do not exist when both measurement methods have been refined for decades and confirmed by independent teams using different instruments. The number 67 comes from the universe's baby picture. Satellite observations of the cosmic microwave background show temperature fluctuations that encode the early universe's properties with extraordinary precision. These measurements feed into the lambda CDM standard model of cosmology. Lambda represents dark energy. CDM stands for cold dark matter. This model successfully explains how structure formed, why galaxies cluster in certain patterns, and how light elements were created after the Big Bang. Lambda CDM makes a clear prediction. If you start with the universe as it appeared 380,000 years after the Big Bang and let it evolve forward under known physics, today's expansion rate should equal 67.4 km per second per megaparsec. The uncertainty on this prediction is remarkably small, less than 1%. Planck satellite data constrains the early universe properties so tightly that wiggle room barely exists. The number 74 comes from measuring the universe today. Cepheid variable stars reveal distances to galaxies. Type Ia supernovae explosions provide independent distance checks. Redshift measurements show how fast galaxies recede from us. Combine these observations and you get 73 to 74 km per second per megaparsec, depending on the exact dataset. Hubble measured this. Webb confirmed it. The uncertainty here is also small, around 2 to 3%. These measurements should match. They describe the same physical quantity, how fast space expands. Yet they disagree by 7 km per second per megaparsec. Both cannot be correct if standard physics applies throughout cosmic history. Something must give. One option is that early universe measurements mislead us. Perhaps subtle systematics affect cosmic microwave background analysis in ways we have not recognized. Temperature maps might contain contamination from foreground emissions that bias the results. Extraction of cosmological parameters might involve incorrect assumptions about how acoustic waves behaved in the primordial plasma. Another option is that present-day measurements contain hidden errors. Maybe Cepheid distances have small calibration problems that accumulate across billions of light-years. Maybe type Ia supernovae explosions vary more than we realize, introducing scatter into distance estimates. Maybe interstellar dust affects measurements in ways not fully corrected. Yet the most likely explanation is new physics. Something exists that current models do not include. This something could be early dark energy that injected extra expansion right after the Big Bang. It could be exotic particles that modify gravity's behavior on cosmic scales. It could be evolving dark energy that changes strength over time. It could be physics we have not even imagined yet. The 74 versus 67 problem was not supposed to happen. Lambda CDM cosmology seemed settled. It explained so many observations so well that most scientists considered the universe's broad-scale behavior understood. Details remained to be filled in, but the overall picture appeared solid. This tension cracks that foundation. Mark Kamionkowski, a theoretical cosmologist at Johns Hopkins University, stated that theorists now have license to get creative. Exotic particles, changing electron masses, primordial magnetic fields, strange dark matter properties, ideas that seemed unnecessary before now deserve serious consideration. The data demands explanations beyond standard physics. Every new measurement makes the problem worse instead of better. Researchers hoped improved instruments would reveal that one method or the other contained errors. Instead, improved instruments make both measurements more certain. The gap persists. The crisis deepens. This is not some obscure detail affecting only specialists. The Hubble constant determines the universe's age, size, and fate. It governs how fast galaxies separate from each other and how long cosmic structure had to form. If we cannot measure this number correctly, our entire cosmic timeline becomes questionable. The timeline becomes especially questionable when galaxies appear where they have no right to exist. Astronomer Erica Nelson at the University of Colorado Boulder called them bananas. 6 galaxies appeared in Webb's first deep field images from a time just 500 to 700 million years after the Big Bang. These were not the faint, small proto-galaxies that theory predicted. They blazed bright red in Webb's infrared cameras. When researchers calculated their masses, the numbers seemed impossible. Each galaxy contained nearly as many stars as the modern Milky Way galaxy. The term universe breakers emerged because these galaxies should not fit into the standard cosmological model. Lambda CDM predicts how quickly structure forms in the early universe. Dark matter clumps together gradually under gravity. Normal matter falls into these dark matter wells and begins forming stars. The process takes time. Small structures merge into larger ones. This hierarchical assembly builds galaxies over hundreds of millions to billions of years. Yet here sat 6 massive galaxies fully formed when the cosmos was only 5% of its current age. The universe had existed for less than 1 billion years. That should not have given enough time to assemble so much mass into such organized structures. Ivo Labbé, from Swinburne University of Technology in Australia, led the discovery team. He described expecting to find baby galaxies and instead discovering monsters. Adding up all the stars in these 6 galaxies exceeded what the universe should have contained at that time. The Big Bang started with hydrogen and helium. Heavier elements came later from stars fusing lighter elements and exploding. The total amount of matter available to form stars was limited by cosmic expansion and cooling. These 6 galaxies seem to have captured and condensed more material than existed in their cosmic neighborhood. 3 explanations existed. First, maybe the galaxies were not actually as massive as they appeared. Perhaps supermassive black holes at their centers contributed significant light that researchers mistook for starlight. Black holes consuming gas emit tremendous radiation. If black hole light dominated what Webb saw, the stellar mass estimates would be overinflated. Second, maybe stars formed much more efficiently in the early universe than they do today. Modern star formation is wasteful. Most gas in galaxies never becomes stars. It gets heated, blown away by stellar winds, or simply fails to condense densely enough. Early galaxies might have converted gas to stars at far higher rates. If the star formation efficiency approached 100% instead of today's few percent, massive galaxies could form faster. Third, maybe cosmology needs serious revision. If dark matter accumulated into large halos faster than standard models predict, it would pull in normal matter more rapidly. This requires changes to either how dark matter behaves or how structure forms on large scales. Both options upend significant portions of current theory. The discovery sent shockwaves through the astronomical community. Researchers scrambled to confirm the findings using spectroscopy. Initial observations used imaging alone. Light gets redshifted as it travels through expanding space, making distant objects appear redder. Measuring exact redshift requires splitting light into its component wavelengths. This spectroscopic confirmation would prove the galaxies truly existed at those early times, rather than being intrinsically red objects from later eras. Some spectroscopic data came back positive. The galaxies appeared as old as estimated. Their light had indeed traveled for over 13 billion years. Other candidates turned out to be less massive than initially thought, or slightly younger than estimated. But several universe breakers held up under scrutiny. Joel Lager from Penn State University, a co-author on the discovery, stated this revelation upends what many considered settled science. The idea that massive galaxies formed extremely early in cosmic history challenges fundamental assumptions. Cosmology textbooks describe gradual structure growth. These observations show rapid assembly instead. The universe breakers forced a reckoning. Either our models of galaxy formation contain major blind spots, or unknown physics operates in the early universe. Neither option was comfortable. Both demanded new thinking about how the cosmos evolved. What made the situation stranger was finding even more problematic objects hidden in the data. The universe, at age 500 million years, should have been simple. Dark matter halos were small, fragmented, and loosely organized. Stars had just begun igniting in tiny pockets where gas clouds collapsed under gravity. Galaxies, if they existed at all, should have been chaotic collections of a few million stars at most. No large-scale structure, no spiral arms, no organized rotation, just turbulent gas and scattered starlight. Webb looked at this epoch and found fully developed galaxies with masses exceeding 100 billion times our solar mass. These were not primitive assemblages. They showed signs of mature stellar populations. Their light contained signatures of stars that had already lived and died, enriching gas clouds with heavy elements. Star formation had been ongoing for some time already. The problem goes deeper than just total mass. These galaxies appeared compact and dense. Modern galaxies of similar mass spread across hundreds of thousands of light years. The early galaxies Webb discovered packed equivalent masses into regions 10 times smaller. This density implies gravitational wells far stronger than expected. Dark matter concentrations had to be extreme. How could dark matter accumulate so rapidly? The standard cosmological model describes dark matter as cold, meaning its particles move slowly compared to light speed. Cold dark matter clumps gradually because it lacks pressure support. It cannot quickly collapse into dense concentrations. It must fall together under gravity over extended time periods. Simulations show this process requiring billions of years to create the dark matter halos needed for massive galaxies. Unless dark matter behaved differently in the early universe, some physicists now consider warm dark matter or even hot dark matter scenarios. If dark matter particles moved faster than assumed, they might collapse and condense differently. This would alter structure formation timelines dramatically. However, warm and hot dark matter create other problems. They struggle to explain observations of the cosmic microwave background and current galaxy distributions. Another puzzle involves the stars themselves. Creating 100 billion solar masses of stars requires converting enormous amounts of hydrogen gas. That gas must cool enough to collapse under gravity. Modern galaxies cool gas slowly because star formation injects heat back into surrounding material. Supernova explosions, stellar winds, and radiation from young stars all heat gas and prevent further star formation. This feedback regulation limits how quickly galaxies grow. Early galaxies might have avoided these limitations. Perhaps gas in the early universe cooled more efficiently because it contained fewer heavy elements. Heavy elements radiate energy effectively, helping gas clouds lose heat. Yet primordial gas was almost pure hydrogen and helium, poor at radiating. This seems like it should slow star formation, not accelerate it. Or maybe the early universe was denser overall. Higher density means stronger gravity. Stronger gravity compresses gas more forcefully, overwhelming outward pressure from heating. Stars could form faster because gravity dominated more completely. The gas had nowhere to escape. It had to condense and ignite whether feedback tried to stop it or not. Stellar ages posed another question. Some of these galaxies showed evidence of multiple stellar generations. You need time for first-generation stars to form, live, explode, and enrich gas with heavy elements before second-generation stars ignite. Yet all of this apparently happened in just a few 100 million years. Modern stellar evolution timelines suggest this schedule seems impossibly compressed. The galaxies Webb discovered were not just large, they were mature, they had histories, they had evolved through stages that should take billions of years. Cramming that evolution into the universe's first 500 million years broke the accepted paradigm of gradual cosmic development. No one expected galaxies to fast-track like this. The hierarchical assembly model of structure formation dominated cosmology for decades. Small objects form first, then merge into progressively larger structures over time. These Webb observations suggest a different path, one where some galaxies assembled almost immediately. What could drive such rapid assembly? What physics was missing? The answer might lie in strange, compact objects glowing red against the cosmic darkness. Formation scenarios cannot account for what Webb detected. Standard galaxy formation follows predictable steps. First, dark matter fluctuations in the early universe grow under gravity. These fluctuations become small, dark matter halos. Gas falls into the halos and cools. Cooling gas fragments into molecular clouds. These clouds collapse into the first stars. Stellar radiation ionizes surrounding gas, heating it and slowing further star formation. Over time, small halos merge into larger ones. Their galaxies merge too, building mass through accretion and collision. This hierarchical process requires time. Simulations of structure formation run on supercomputers show galaxy growth spanning billions of years. Massive galaxies form late in cosmic history, not early. The biggest galaxies today assembled through countless mergers of smaller predecessors. Their growth trees branch backward through time to hundreds of small progenitors. The fast-track galaxies Webb found skipped most of these steps somehow. They appeared massive and mature far earlier than simulations can reproduce. Something accelerated their formation dramatically. Three main theories attempt to explain this acceleration. Theory 1 involves supermassive black hole seeding. If the early universe created black holes with masses thousands to millions of times our stellar mass right away, these could anchor galaxy formation. Gas would stream into the black hole's gravitational well rapidly. The infalling gas would fragment into stars. A massive galaxy could build quickly around a massive black hole seed. However, we have no confirmed mechanism for creating such massive black holes so early. Stellar collapse produces black holes of only tens of solar masses. Theory 2 proposes super-efficient star formation. Perhaps early galaxies converted gas into stars at rates approaching 100% efficiency. Every bit of gas that fell into the dark matter halo became a star, instead of being blown away by feedback. This conflicts with everything we observe about star formation. Modern regions where stars form waste most of their gas. Only 1 to 10% becomes actual stars. The rest disperses. Why would early galaxies operate so differently? Theory 3 suggests fundamentally different dark matter physics. If dark matter interacts with itself through forces we have not detected, it might collapse faster than cold dark matter models predict. Self-interacting dark matter could create dense halos early in cosmic history. These halos would trap gas more effectively and trigger rapid star formation. Detecting evidence for dark matter self-interactions remains an active research area with no definitive results yet. Each explanation requires adding new physics beyond the standard cosmological model. None explains observations using only lambda CDM. This creates a serious problem because lambda CDM succeeds at explaining so many other phenomena: the cosmic microwave background, galaxy clustering, element abundances, gravitational lensing statistics. Lambda CDM handles all of these correctly. Modifying the model to accommodate fast-track galaxies risks breaking these other successes. Some researchers suggested an alternative. Maybe Webb was not seeing galaxies at all. Perhaps some of these bright red objects are not dominated by starlight. Quasars powered by supermassive black holes emit tremendous radiation across all wavelengths. If the light comes primarily from black hole accretion rather than stars, mass estimates would be wrong. The objects would be smaller, less massive, and less problematic for cosmology. Follow-up observations tested this idea. Spectroscopy revealed emission lines characteristic of both stars and active black holes in many of these galaxies. Both components contributed to the total light. Some objects showed stronger black hole signatures than others. This created a spectrum from star-dominated galaxies to black hole-dominated quasi-stellar objects. Yet even after accounting for black hole contamination, many fast-track galaxies remained too massive for their age. Their stellar masses exceeded predictions by factors of 5 to 10. Models could not be adjusted enough to explain the discrepancy without breaking other predictions. The mystery persisted even after careful analysis separated starlight from black hole emission. The fast-track problem represents more than just unusual objects. It suggests our entire picture of how galaxies form might miss crucial physics. Whatever process built these early massive galaxies operated differently than modern galaxy formation. Either conditions in the early universe enabled faster assembly, or hidden mechanisms accelerated growth beyond standard predictions. The search for these mechanisms led to the discovery of something even stranger. Astronomers named them for their appearance in Webb's images, tiny crimson points scattered across the deep field. Little red dots showed up in the CES survey, the Cosmic Evolution Early Release Science Program. Researchers initially assumed these were extremely distant galaxies. Their red color indicated high redshift. Light from far away gets stretched to longer, redder wavelengths by cosmic expansion. Red objects typically mean distant objects. When spectroscopy measured their distances, the little red dots confirmed their extreme remoteness. They existed during the universe's first billion years. Their small, apparent sizes suggested compact structures. Here is where things turned strange. Their brightness implied enormous masses. Objects that small should not shine that brightly unless they packed extraordinary numbers of stars into tiny volumes. The brightness-to-size ratio did not make sense. Astronomers calculated the stellar mass needed to produce the observed light. The numbers came back enormous. Yet fitting that many stars into such small regions created density problems. The stars would orbit so closely together that interactions would tear apart any organized structure. The systems should be unstable. Then researchers looked more carefully at the light spectra. Emission lines appeared that do not come from stars. These lines indicate hot gas swirling around black holes. The gas accelerates to tremendous velocities as it spirals inward. Friction heats it to millions of degrees. At these temperatures, atoms lose electrons and emit characteristic radiation at specific wavelengths. The spectra showed these signatures clearly. The little red dots contain actively feeding supermassive black holes. Much of their brightness comes from black hole accretion, not starlight. When scientists removed the black hole contribution, the stellar masses dropped dramatically. What appeared to be galaxies with 100 billion stellar masses turned out to be galaxies with perhaps 10 billion stellar masses hosting brilliant black holes. This solved one problem but created another. How did supermassive black holes form so early? A black hole massive enough to shine this brightly contains millions to billions of times our stellar mass. Growing to that size requires consuming vast amounts of matter. Black holes accrete material at limited rates determined by radiation pressure. The radiation from infalling matter pushes against additional material trying to fall in. This creates an upper limit on growth speed called the Eddington limit. Even at the maximum Eddington limited accretion rate, growing a supermassive black hole takes significant time. You must start with a seed black hole of at least hundreds of solar masses. Then that seed must accrete continuously at maximum rates for hundreds of millions of years. The timeline barely fits into the universe's first billion years. Any interruption in accretion or slower growth rates make the process impossible. Theories for forming massive seed black holes include direct collapse of gas clouds in the early universe. Under special conditions, gas clouds might collapse directly into black holes without forming stars first. This could create seed masses of thousands to hundreds of thousands of solar masses immediately. These heavy seeds could then grow to supermassive scales, quickly enough to explain little red dots. Another theory involves runaway collisions in dense star clusters. If stars pack tightly enough together, they collide and merge before supernovae can disperse them. A growing central object sweeps up more and more stars. Within a few million years, this process could build a black hole seed of thousands of solar masses. However, creating the necessary density requires extreme conditions rarely achieved. The little red dots do more than challenge black hole formation models. They contaminate galaxy mass estimates across the early universe. Any red compact object could be a galaxy or a black hole-dominated system. Distinguishing between them requires spectroscopy, which takes far more time than imaging. Most high redshift galaxy surveys rely on imaging alone. This means published galaxy mass estimates potentially include significant black hole contamination. When researchers carefully removed all little red dot candidates from galaxy mass counts, the early universe became less problematic for cosmology. Many apparent universe breakers were actually little red dots. The Standard Model survived this particular challenge, yet problems remained. Even after removing black hole-dominated objects, roughly twice as many massive galaxies existed in the early universe than Lambda CDM predicts. The discrepancy shrank from factors of 10 to factors of 2. Better, but still unexplained. The little red dots revealed another truth about the early cosmos. Black holes and galaxies grew together from the beginning. The oldest quasars blaze from an era when the universe was less than 10% its current age. Quasars are supermassive black holes, consuming materials so rapidly that they outshine entire galaxies. The falling matter reaches temperatures of millions of degrees. It radiates across all wavelengths from radio waves to X-rays. These brilliant beacons can be detected billions of light years away, allowing astronomers to study black hole growth in the early universe. Webb has found quasars existing just 600 million years after the Big Bang. Their black holes contain masses reaching billions of times our stellar mass. This timeline creates severe problems. Black holes grow by accreting matter. Accretion heats material and generates radiation. That radiation pushes outward against the inward pull of gravity. When radiation pressure balances gravitational pull, accretion reaches its maximum sustainable rate. This maximum rate is the Eddington limit. A black hole starting with 100 solar masses can grow to roughly 200 solar masses in 10 million years at the Eddington limit. Doubling takes about 10 million years regardless of starting mass. To grow from 100 solar masses to 1 billion solar masses requires roughly 30 doubling times. 30 times 10 million years equals 300 million years. The oldest quasars appeared in the universe's first 600 million years. If black hole growth began immediately after the Big Bang, continuous Eddington limited accretion could barely reach the required masses. Any delay in starting or any period of reduced accretion makes the timeline impossible. The black holes must have either started more massive than stellar collapse black holes typically are, or they accreted faster than the Eddington limit allows. Super-Eddington accretion happens when inflow overwhelms radiation pressure. Gas falls inward faster than radiation can push it away. This requires specific geometries or dense environments that trap radiation. Some simulations show early black holes could achieve super-Eddington accretion under the right conditions. Dense gas clouds in the first galaxies might have provided these conditions. However, direct observational evidence for super-Eddington growth remains limited. Alternatively, Massive seed black holes could have formed through direct collapse mechanisms. Instead of forming from stellar remnants weighing tens of solar masses, these seeds could start at thousands to hundreds of thousands of solar masses. With such massive starting points, reaching billions of solar masses within 600 million years becomes achievable. The challenge is explaining how direct collapse happens. Direct collapse requires pristine gas clouds never enriched by earlier star formation. Heavy elements help gas cool efficiently. Cooling triggers fragmentation. Fragmentation produces stars instead of black holes. To get direct collapse, you need gas that remains too hot to fragment. This occurs in clouds composed of pure hydrogen and helium exposed to strong radiation from nearby sources. The radiation keeps the gas warm enough to resist fragmentation while gravity pulls it together. The cloud collapses as a whole, forming a massive black hole seed. Webb observations support the existence of these conditions. Early galaxies showed star formation occurring in environments bathed in intense radiation from neighboring young galaxies. These regions could host direct collapse black hole formation. Whether this process occurred frequently enough to explain all early quasars remains under investigation. Another mystery involves the growth itself. Continuous Eddington limited accretion assumes a steady supply of inflowing material. Where does all this gas come from? Quasars consume material at rates of several stellar masses per year. Over hundreds of millions of years, this totals billions of solar masses of fuel. Early galaxies must have contained enormous gas reservoirs to feed their central black holes. Webb detected these reservoirs. Observations reveal vast amounts of molecular gas in early galaxies hosting quasars. The gas masses often exceed the stellar masses by factors of 10 or more. These systems are gas-rich in ways modern galaxies never achieve. Cosmic expansion was slower in the early universe, allowing gas to remain bound to galaxies more easily. Mergers between galaxies funneled additional gas towards central regions where black holes could consume it. The black holes did more than just grow. Their activity shaped their host galaxies profoundly. Radiation and winds from the quasar pushed against surrounding gas. This feedback heated gas clouds and prevented them from cooling to form stars. Observations show galaxies hosting the most massive black holes often have suppressed star formation despite abundant gas supplies. This creates a self-regulating cycle. Black holes grow by consuming gas. Their growth generates energy that heats remaining gas. Heated gas cannot form stars and may not fall into the black hole efficiently. Growth slows. Eventually, conditions settle and accretion resumes. This cycle might explain why black holes and galaxies maintain specific mass relationships. The relationship between black hole mass and galaxy mass hints at deeper connections still being uncovered. When astronomers added up all the stellar masses in early galaxies, the numbers exceeded what should have existed. The Big Bang created hydrogen and helium almost exclusively. Trace amounts of lithium formed as well. Everything heavier came later from stars. Stars fuse hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the periodic table. When massive stars explode as supernovae, they scatter these heavy elements into space. The next generation of stars incorporates this enriched material. The first stars contained no heavy elements at all. They were pure hydrogen and helium. These population 3 stars remain theoretical because none have been directly observed yet. They should have been massive, bright, and short-lived. Their explosions would have seeded the universe with the first metals, where astronomers define metals as any element heavier than helium. Creating stars requires cooling gas. In the modern universe, heavy elements help gas cool efficiently by radiating away energy. Primordial gas lacked these elements. It could only cool through molecular hydrogen radiation, a far less efficient process. This suggests the first stars formed in limited numbers and required very specific conditions. Yet when Webb looked at galaxies from the universe's first billion years, it found stars everywhere. Galaxies contained tens to hundreds of billions of stellar masses worth of stars. The total stellar mass density in the early universe exceeded predictions by factors of 2 to 10 depending on the exact epoch examined. Where did all this mass come from? The universe's total matter content is fixed by Big Bang nucleosynthesis and cosmic microwave background observations. Dark matter makes up about 83% of all matter. Normal baryonic matter makes up the remaining 17%. This baryonic matter was initially almost all gas. Stars form by converting gas into stellar material. The efficiency of this conversion determines how many stars exist at any given time. Modern observations show that only about 10% of available gas becomes stars. The rest remains in gaseous form or gets expelled from galaxies by supernova-driven winds. If early galaxies converted gas to stars at the same efficiency, there should not be enough stellar mass to explain Webb's observations. Increasing star formation efficiency helps, but creates new problems. If early galaxies turned 50% of their gas into stars instead of 10%, where did the remaining gas go? Modern galaxies contain substantial gas reservoirs. Early galaxies should have even more gas because less time had passed for star formation to consume it. Yet, observations suggest early galaxies were remarkably efficient at making stars, leaving little gas behind. Another issue involves stellar lifetimes. Massive stars live only millions of years before exploding. Lower mass stars, like our Sun, live billions of years. The stellar mass we observe today in distant galaxies represents what existed when their light left them billions of years ago. Some of those stars would have already died by now. When we calculate stellar mass from galaxy brightness, we estimate the living stellar population at that moment. Dead stars no longer contribute to brightness, but their mass still existed. This means the total mass converted into stars over time exceeds what we measure as current stellar mass. Gas formed stars, those stars died, and new stars formed from enriched gas. Each generation of star formation consumed more of the available baryonic mass. Accounting for all these generations increases the total baryonic mass requirement even further. Simulations of galaxy formation struggle to reproduce the high stellar masses Webb observes. These simulations start with initial conditions from the cosmic microwave background. They evolve dark matter and baryonic matter forward in time under gravity, gas dynamics, and star formation prescriptions. The prescriptions include how gas cools when it forms stars, and how feedback from stars affects surrounding material. Even with optimistic assumptions about star formation efficiency and suppressed feedback, simulations produce lower stellar masses than observed. Something about early galaxy formation operates differently than our models capture. Either gas cooled faster, stars formed more efficiently, feedback was weaker, or some combination of all three occurred. The mass problem might also indicate that our understanding of dark matter halos is incomplete. If early dark matter halos were more massive or concentrated than predicted, they would have deeper gravitational wells. Deeper wells attract more gas. More gas means more stars. Perhaps dark matter physics differs from standard cold dark matter assumptions in ways that become important at high redshifts. Every explanation requires revising some aspect of standard cosmology or astrophysics. The observations leave little room for measurement error. Webb spectroscopic conformations verify the distances and ages. The stellar masses derive from well-understood stellar physics. The discrepancy is real. The universe formed more stars earlier than expected. This changes our understanding of cosmic history fundamentally. It suggests the universe transitioned from dark to light-filled more rapidly than thought. Star formation ignited everywhere almost simultaneously rather than gradually building over time. The true scale of this star formation becomes clear when viewing the largest galaxy maps ever created. Nearly 800,000 galaxies fill a single Webb telescope image. The Cosmos Webb survey observed a patch of sky in the constellation Sextans. This region measures roughly 2.5 times the full moon's apparent size. To human eyes, it appears empty except for a few foreground stars from our galaxy. Webb revealed the truth. Galaxies pack this region so densely that they nearly touch each other in the image. Every direction contains distant starlight. The survey required 200 hours of Webb's observation time, the largest allocation given to any program in the telescope's first year. Nearly 50 researchers from institutions worldwide collaborated on the project. They stitched together more than 10,000 individual exposures to create the final panorama. The resulting image captures galaxies across nearly all cosmic time. Some galaxies appear as they existed 13 billion years ago, just 500 million years after the Big Bang. Others show the universe at intermediate ages, when it was 3, 5, or 8 billion years old. The nearest galaxies in the image exist in relatively recent cosmic history, their light traveling only a few billion years to reach us. This time, depth creates a three-dimensional map showing how galaxies evolve across cosmic epochs. Previous surveys using Hubble covered similar areas but detected far fewer galaxies. Webb's infrared vision penetrates dust that blocks visible light. It sees galaxies too faint or too red for Hubble to detect. The galaxy count increased tenfold compared to earlier surveys of the same sky region. Most of these newly discovered galaxies existed during the universe's first few billion years. The Cosmos Webb team made all their data publicly available immediately. Amateur astronomers can access the same images professional researchers use. Interactive tools allow anyone to explore the galaxy catalog, zoom into individual objects, and investigate their properties. This democratization of cutting-edge astronomical data represents a significant shift in how science operates. Within the Cosmos Webb field, researchers identified galaxy clusters containing hundreds to thousands of individual galaxies bound together by gravity. These clusters act as gravitational lenses, bending light from even more distant galaxies behind them. The lensing creates multiple images of background galaxies, stretched and distorted into arcs and rings. Over 100 strong gravitational lenses appeared in the Cosmos Webb data, each one enabling detailed study of extremely distant objects. The galaxy colors span the full rainbow from blue to deep red. Blue galaxies actively form stars. Young hot stars emit blue light copiously. Red galaxies have mostly stopped star formation. Their stellar populations consist of older, cooler stars that emit red light. The color distribution shows that star formation activity peaks at intermediate times in cosmic history, then declines toward the present day. Tracking individual galaxies across the Cosmos Webb field reveals how galaxy properties change with cosmic time. Early galaxies tend to be smaller, more irregular, and more actively forming stars than modern galaxies. As time progresses, galaxies grow larger through mergers. Their star formation rates decline. Spiral structures emerge. The transition from chaotic early galaxies to organized modern galaxies plays out across the data. Supermassive black holes appear throughout the field as well. Some galaxies host actively feeding black holes that outshine their stellar populations. These active galactic nuclei appear as bright point sources surrounded by fainter galaxy emission. Other black holes remain dormant, invisible except through their gravitational influence on surrounding stars and gas. The Cosmos Webb survey also captured time-variable objects. Supernovae exploded during the survey, their brightness changing between observations. Some of these supernovae occurred in galaxies so distant that the universe was less than 2 billion years old when the stars exploded. Studying ancient supernovae helps calibrate cosmic distances and measure expansion rates across time. Type Ia supernovae serve as standard candles because they reach predictable peak brightness. Observing them at multiple redshifts traces the universe's expansion history. Cosmos Webb detected roughly 80 supernovae in early universe galaxies, 10 times more than previous surveys had found. This sample allows precise measurements of how expansion rates evolved as the universe aged. The sheer number of galaxies in Cosmos Webb creates statistical power. Rare objects that might appear only once in smaller surveys show up multiple times here. Strange transitional galaxies, unusual black hole systems, extreme starbursts, The large sample contains examples of nearly every evolutionary stage and galaxy type. Cosmos Webb represents just the beginning. The survey covered less than 1/10,000th of the whole sky. Extrapolating from this region suggests hundreds of billions of galaxies exist across the observable universe. Each contains billions to trillions of stars. Each has its own history of formation, evolution, and eventual fate. The image also hints at structure on the largest cosmic scales. Galaxies do not distribute randomly. They trace invisible scaffolding built from dark matter. James Webb sees wavelengths of light invisible to human eyes and to Hubble. Infrared radiation has longer wavelengths than visible light. Our eyes detect wavelengths from about 400 nanometers for violet light to 700 nanometers for red light. Infrared starts at 700 nanometers and extends to hundreds of thousands of nanometers. Webb observes wavelengths from 600 nanometers out to 28,000 nanometers, spanning near-infrared through mid-infrared. This infrared sensitivity provides three critical advantages for studying the early universe. First, cosmic expansion redshifts all light to longer wavelengths. Light emitted as ultraviolet or blue from distant galaxies arrives at Earth as infrared. The farther away an object lies, the more extreme its redshift becomes. The most distant galaxies shift their light entirely out of visible wavelengths into infrared. Hubble could barely detect them. Webb sees them clearly. Second, infrared penetrates cosmic dust. Dust grains in space absorb and scatter blue light efficiently, but affect red and infrared light much less. Regions hidden behind dust clouds appear dark in visible light, but glow in infrared. Young stars form inside dense dust clouds. Star-forming galaxies often contain substantial dust. Webb's infrared vision lets it see through this dust to the stars forming within. Third, cold objects emit infrared radiation preferentially. Cool dust surrounding stars, molecular clouds where stars form, and even exoplanet atmospheres radiate most of their energy at infrared wavelengths. To detect these objects requires infrared-sensitive instruments. Visible light telescopes miss them entirely. Webb's primary mirror measures 6.5 meters across, almost 3 times Hubble's diameter. Larger mirrors collect more light and achieve better resolution. This combination of size and infrared sensitivity makes Webb extraordinarily powerful for studying distant and dust-obscured objects. It collects about 6 times more light than Hubble and operates at wavelengths where young galaxies shine brightest. The deepest Webb images integrate light for many hours. The telescope points at a target and exposes its detectors continuously. Faint objects too dim to appear in short exposures gradually build up signal strength. Background noise averages out. After 12 to 20 hours of integration, objects appear that are hundreds of times fainter than anything Hubble could detect in similar time. These deep integrations reveal galaxies at the edge of the observable universe. Light from these galaxies has traveled for over 13 billion years. The universe was less than 5% its current age when this light began its journey. We see these galaxies as they appeared in their infancy, just forming their first stars, unaffected by billions of years of subsequent evolution. The wavelength coverage of Webb's instruments enables precise measurements of galaxy properties. By observing the same galaxy at multiple infrared wavelengths, astronomers reconstruct its spectrum. The spectrum reveals which types of stars dominate, how much dust is present, whether active star formation continues, and numerous other physical properties. Hubble could measure colors using a few broad filters. Webb measures detailed spectra across dozens of wavelength channels. Mid-infrared observations particularly excite researchers. Wavelengths from 5 to 28 microns contain diagnostic features that reveal molecular abundances in galaxies. Polycyclic aromatic hydrocarbons, complex organic molecules abundant in space, emit characteristic radiation at mid-infrared wavelengths. Their presence indicates specific physical conditions in galaxies. Webb's MIRI instrument is the first space telescope capable of high-resolution mid-infrared imaging and spectroscopy. The infrared universe looks different from the visible universe. Galaxies that appear bright in visible light sometimes fade at infrared wavelengths. Others, invisible to visible light telescopes, dominate infrared images. This wavelength-dependent appearance reflects different physical processes. Visible light traces hot, young stars. Infrared traces dust warmed by star formation or emission from cool stellar populations. Webb operates at the second Lagrange point, 1.5 million kilometers from Earth, on the side opposite the solar system. This location keeps the telescope in Earth's shadow permanently. Staying cold is essential for infrared astronomy. Warm objects emit their own infrared radiation that would swamp faint signals from distant sources. Webb's sunshield maintains temperatures below 50 Kelvin on the telescope side, cold enough that the telescope's own thermal emission stays minimal. Every observation confirms Webb's extraordinary capabilities. Objects predicted to be barely detectable appear clearly. Galaxies expected to show only rough shapes reveal internal structures. The early universe emerges from obscurity in unprecedented detail. That detail shows something unexpected about the foundation everything rests upon. Ordinary matter makes up less than 5% of the universe's total mass and energy. Dark matter contributes 27%. Dark energy fills the remaining 68%. We can see ordinary matter directly because it emits, absorbs, or scatters light. Dark matter does none of these things. It passes through regular matter without interacting electromagnetically. It does not form atoms. It cannot bond into molecules. It exists as ghostly particles that respond only to gravity. Yet dark matter shapes the entire cosmic structure. Without it, galaxies would fly apart. Their stars orbit so quickly that visible matter alone cannot provide enough gravity to hold them together. Dark matter halos surrounding galaxies supply the additional gravitational binding. These halos extend far beyond visible galaxy edges, creating reservoirs of mass invisible to telescopes. On larger scales, dark matter organizes into a three-dimensional web spanning the universe. This cosmic web formed from tiny density fluctuations in the very early universe. Regions with slightly more dark matter than average attracted additional dark matter through gravity. These overdense regions grew denser over time. Underdense regions became voids as matter evacuated toward higher density areas. The result resembles a sponge. Dense nodes of dark matter sit at the intersections of long filaments. The filaments stretch across tens to hundreds of millions of light years. Between filaments lie vast voids containing very little matter. Galaxies form primarily within filaments and at their intersections. The cosmic web structure thus determines where galaxies exist. Computer simulations of structure formation reproduce this web-like pattern. Starting from initial conditions measured in the cosmic microwave background, simulations evolve dark matter forward in time under gravity alone. No other forces affect dark matter according to standard cold dark matter models. Gravity makes overdense regions denser and underdense regions emptier. After billions of years of evolution, simulations show the characteristic web structure matching observations. Observing the dark matter web directly poses challenges because dark matter does not emit light. Astronomers use two techniques to map it anyway. First, they observe where galaxies exist. Galaxies trace dark matter distribution because they form in dark matter halos. The galaxy distribution reveals the underlying dark matter scaffolding. This technique works well but shows only dark matter locations dense enough to form galaxies. The second technique uses gravitational lensing. Massive objects curve spacetime according to Einstein's general relativity. Light follows curved spacetime paths. When light from a distant galaxy passes near a foreground dark matter concentration, its path bends. This bending distorts the background galaxy's image, stretching and magnifying it. By measuring these distortions across many background galaxies, astronomers reconstruct the foreground dark matter distribution. Webb's latest dark matter map used gravitational lensing applied to nearly 800,000 galaxies from the Cosmos Webb survey. Each galaxy's shape measured carefully. Comparison with intrinsic shapes expected for galaxies at those distances revealed distortions caused by intervening dark matter. The cumulative effect of all these measurements built a two-dimensional projection of the three-dimensional dark matter distribution. The map shows extraordinary detail. Dense clusters of dark matter appear as bright blue regions in visualizations. Filaments connect these clusters, creating the web-like pattern. Some filaments stretch across the entire field of view, spanning tens of millions of light-years. Other, shorter filaments branch between nearby clusters. The structure appears hierarchical, with smaller subfilaments feeding into larger ones. Comparing dark matter maps to galaxy locations shows remarkable agreement. Wherever dark matter concentrates, galaxies appear. Wherever dark matter forms filaments, galaxies line up along those filaments like beads on a string. The correlation approaches 100% for large-scale structures. Dark matter and ordinary matter co-evolved throughout cosmic history, never separating despite their different properties. This co-evolution makes sense from a physics standpoint. Dark matter's gravity attracts ordinary matter. Ordinary matter falls into dark matter halos and filaments. There it can cool, condense, and form stars. Without dark matter providing gravitational wells, ordinary matter would remain diffusely spread with insufficient density to collapse and form galaxies. Dark matter created the framework. Ordinary matter filled it in. The cosmic web evolved over time. Early in cosmic history, it was more uniform and less structured. Filaments were thinner and shorter. Clusters were smaller and less dense. As time progressed, structure became more pronounced. Filaments lengthened and thickened. Clusters grew more massive. The web became more defined and hierarchical. Webb's observations trace this evolution by examining dark matter at different distances. Light from nearby objects shows the present-day web structure. Light from distant objects shows the web as it appeared billions of years ago. Comparing these views reveals how the web assembled over time. The findings confirm cosmological simulations remarkably well. The web structure Webb observes matches simulated web structures almost exactly. This agreement validates the Lambda CDM model's predictions about dark matter and structure formation, at least on large scales. Yet mysteries remain about what precisely dark matter consists of and how it behaves on small scales. Before the first stars ignited, dark matter already organized the universe. The cosmic microwave background shows the universe at age 380,000 years. At that time, matter distributed almost uniformly across space. Temperature variations amounted to only 1 part in 100,000. These tiny variations traced density fluctuations that would seed future structure, but structure had not yet formed. No stars existed. No galaxies existed. Just expanding hot plasma, gradually cooling toward neutrality. Dark matter behaved differently than ordinary matter during this era. Ordinary matter remained coupled to radiation through constant electromagnetic interactions. Photons scattered off electrons continuously, preventing matter from clumping too aggressively. This radiation pressure resisted gravitational collapse. Ordinary matter could form sound waves and oscillations, but could not collapse into dense concentrations yet. Dark matter felt no radiation pressure. It interacted only through gravity. As soon as density fluctuations appeared in the early universe, dark matter began collapsing into them. While ordinary matter oscillated, dark matter fell together. By the time the universe became transparent and radiation decoupled from matter, dark matter had already built significant structure. This head start gave dark matter a crucial advantage in structure formation. When ordinary matter finally decoupled from radiation and could respond to gravity freely, it fell into gravitational wells already created by dark matter. The ordinary matter did not need to build structure from scratch. It simply followed dark matter into pre-existing concentrations. Simulations show this process in detail. They start with initial density fluctuations matching cosmic microwave background observations. Dark matter particles move under gravity alone. Their trajectories determine where dark matter accumulates. Within a few 100 million years after the Big Bang, dark matter had formed halos with masses thousands to millions of times our stellar mass. These mini-halos became sites of the first star formation. Ordinary matter streamed into these dark matter halos along filaments already laid down by dark matter. The filaments channeled gas from surrounding regions toward halo centers. This concentrated gas to densities where cooling could finally overcome heating from compression. Molecular hydrogen formed, radiating energy and allowing gas temperatures to drop below 1000 Kelvin. At these temperatures, gravity overwhelmed thermal pressure and gas clouds collapsed into stars. The first stars ignited when the universe was roughly 100 to 200 million years old. They formed in the densest dark matter halos, where gas accumulated most rapidly. These stars were massive, perhaps 100 to 300 times our stellar mass. They burned hot and bright, living only a few million years before exploding as supernovae. Their explosions enriched surrounding gas with heavy elements, enabling the next generation of stars to form more easily. Dark matter continued shaping structure as stars and galaxies emerged. Small dark matter halos merged into larger ones. Their galaxies merged too. This hierarchical assembly built increasingly massive structures over time. Dark matter provided the gravitational framework throughout. Galaxies could not form or evolve without dark matter scaffolding supporting them. The scaffolding extends to the largest cosmic scales. Superclusters containing tens of thousands of galaxies occupy the densest nodes of the dark matter web. Great walls of galaxies stretch across hundreds of millions of light-years along dark matter filaments. Between these structures lie cosmic voids, regions largely empty of both dark matter and ordinary matter. The voids occupy most of space's volume, even though they contain minimal mass. Life exists because of this scaffolding. Our Milky Way galaxy formed in a dark matter halo, massive enough to retain gas and build a substantial stellar population. That halo sits within the Laniakea supercluster, a massive structure containing 100,000 galaxies. Laniakea formed from dark matter overdensity in our region of space. The dark matter web channels matter flows throughout this region, feeding galaxies and enabling ongoing star formation. Without dark matter, cosmic structure would look completely different. Simulations run with ordinary matter alone produce universes without galaxies. Gas remains too diffuse to collapse efficiently. Small-scale structures that do form lack sufficient mass to retain gas against supernova feedback. They blow themselves apart before building substantial stellar populations. Only the addition of dark matter changes this outcome. The cosmic scaffolding shaped not just where structure formed, but when. Dark matter determined the timeline of galaxy assembly. It controlled how quickly gas cooled and condensed. It governed merger rates between galaxies. Every major cosmic event traces back to dark matter's gravitational influence, organizing ordinary matter into observable structures. Modern observations reveal this scaffolding in stunning detail. Gravitational lensing maps show dark matter filaments connecting galaxy clusters exactly as simulations predict. Galaxy surveys trace large-scale structure following dark matter distributions precisely. The agreement between theory and observation validates our understanding of dark matter's role in cosmic evolution. Some of the largest dark matter structures ever detected now appear in Webb's deepest observations. The longest confirmed dark matter filament measures at least 60 million light-years from end to end. This structure connects to the galaxy cluster Max J 717, one of the most massive clusters known. The cluster contains thousands of galaxies bound together by gravity. Its total mass exceeds several quadrillion times our stellar mass. Most of this mass is dark matter. The cluster sits at a node where multiple cosmic Webb filaments meet. Matter streams along these filaments toward the cluster, feeding its ongoing growth. Astronomers mapped the filament using gravitational lensing. Hubble observations revealed background galaxies distorted by the foreground cluster's gravity, but the distortions extended far beyond the cluster itself. Galaxies hundreds of millions of light-years behind the cluster showed systematic stretching aligned along a specific direction. This alignment indicated a massive structure between us and those background galaxies. By measuring the precise distortions of thousands of background galaxies, researchers reconstructed the foreground mass distribution. The filament emerged clearly. It extended from the cluster outward in a long, narrow stream. The filament's width measured several million light-years. Its length exceeded 60 million light-years, based on how far lensing distortions continued. The filament contains more than half of all matter in the surveyed region. Most of this matter is dark matter, invisible except through gravitational effects. Galaxies line the filament, tracing its path like streetlights along a highway. Gas fills the spaces between galaxies, heated to millions of degrees by gravitational compression. This hot gas emits X-rays detectable by space-based X-ray telescopes. Observing the filament in 3 dimensions required combining lensing data with spectroscopy. Spectra of galaxies along the filament revealed their redshifts. Redshift indicates distance in an expanding universe. Galaxies with similar redshifts lie at similar distances, confirming they physically associate with the filament rather than appearing aligned by chance. The 60 million light-year length represents a minimum estimate. The filament likely extends beyond the surveyed field of view. Finding where it truly ends would require mapping even larger sky areas. Other filaments probably connect to it, creating an even more extensive Webb structure. Current observations capture only a section of the full cosmic Webb network. This filament's mass exceeds predictions from some cosmological simulations. If filaments generally contain this much mass, then more than half of all matter in the universe resides in filamentary structures rather than clusters or voids. This would revise our understanding of cosmic matter distribution. Dark matter might concentrate more heavily in filaments than previously thought. The discovery pushes cosmological models to their limits. Lambda CDM predicts filaments should exist and should connect massive clusters. The predictions match observations qualitatively. Filaments appear where expected, connecting what should be connected. However, quantitative details like exact masses and precise distributions show some discrepancies. The observed filament appears denser than typical simulated filaments. Explaining these discrepancies might require modifying either dark matter properties or our understanding of how structure forms. Self-interacting dark matter could create denser filaments by allowing dark matter particles to exchange momentum, leading to different collapse dynamics. Alternatively, baryonic physics might play larger roles in filament structure than current models include. Filaments act as matter highways, channeling gas from voids into clusters. This gas fuels star formation in galaxies along the way. Galaxies forming in filaments have access to continuous gas supplies flowing past them. This differs from galaxies forming in isolation, which must rely solely on gas they originally captured. Filament galaxies can grow more massive by accreting gas from the cosmic flow. The filament connecting to Max J 717 funnels matter into one of the universe's most massive clusters. The cluster continues growing today, pulling in galaxies and gas from its surroundings. Eventually, it may become one of the largest structures in the universe. Its final mass could exceed 10,000 trillion times our stellar mass, rivaling the biggest clusters that cosmology permits to form. Studying this filament opens windows into understanding cosmic evolution on the largest scales. How quickly do filaments assemble? How much mass do they contain at different cosmic epochs? How do galaxies forming in filaments differ from those forming elsewhere? These questions drive ongoing research using Webb and other observatories. The filament also demonstrates dark matter's reality. No alternative theory explains these observations without invoking substantial amounts of invisible mass. The gravitational lensing precisely matches predictions for a massive dark matter structure. The galaxy motions along the filament indicate tremendous mass, far exceeding visible matter. Dark matter provides the only viable explanation. These cosmic highways connect every major structure in the universe, including the clusters where galaxies congregate in extraordinary numbers. Galaxy clusters mark the intersections of cosmic Webb filaments. At these nodes, dark matter accumulates to tremendous densities. Multiple filaments feed matter into the same location, creating gravitational wells deep enough to trap thousands of galaxies. These systems rank among the universe's most massive structures. Individual clusters can mass as much as several quadrillion solar masses. Most of that mass is dark matter. Only about 15% is ordinary matter, split between stars and galaxies, and hot gas filling space between galaxies. The Coma cluster contains over 1,000 confirmed galaxies within a region roughly 20 million light-years across. It lies relatively nearby, at about 300 million light-years distance. This proximity allows detailed studies of cluster properties. Astronomers have mapped Coma's dark matter distribution through gravitational lensing. They have measured galaxy velocities to determine total mass. They have observed X-ray emission from hot gas to trace ordinary matter distribution. All measurements agree on the cluster's enormous mass. Galaxies orbit within the cluster at speeds exceeding 1,000 kilometers per second. At these velocities, visible matter alone would provide insufficient gravity to prevent escape. The galaxies should fly apart. They remain bound only because dark matter contributes 6 times more mass than visible matter. Without this dark matter, no cluster could exist. Filaments feeding Coma funnel galaxies and gas toward the cluster center continuously. New galaxies fall in regularly, merging with existing cluster members. This process has continued for billions of years. Coma has grown from a small proto-cluster in the early universe to its present massive state through ongoing accretion. When galaxies fall into clusters, their environments change dramatically. The space between cluster galaxies contains extremely hot gas, heated to tens of millions of degrees by gravitational compression. This hot gas exerts ram pressure on infalling galaxies, stripping away their cold gas supplies. Without cold gas, star formation ceases. The galaxies transform from blue and star-forming to red and quiescent. Cluster galaxies also undergo frequent gravitational interactions. Close passes distort galaxy shapes and trigger starbursts through tidal compression. Eventually, many interactions lead to mergers, where galaxies combine into larger systems. The most massive cluster galaxies formed through dozens or hundreds of mergers over time. They sit near cluster centers where interactions occur most frequently. The largest cluster galaxies can exceed 10 trillion solar masses. These behemoths dominate their neighborhoods gravitationally. They continue growing by cannibalizing smaller galaxies that wander too close. Eventually, they may incorporate most of their cluster's stellar mass, though this process takes many billions of years to complete. Webb observations reveal cluster structures at high redshifts when the universe was much younger. These protoclusters contain fewer galaxies than modern clusters. They also show different properties. Proto-cluster galaxies form stars more actively than modern cluster galaxies. Their gas has not yet been stripped away by hot cluster atmospheres. The transition from active star-forming protoclusters to quiescent mature clusters plays out across cosmic time. One remarkable discovery involves finding protoclusters at redshifts beyond 6, corresponding to times less than 1 billion years after the Big Bang. These early structures contain dozens of galaxies concentrated in relatively small regions. They represent seeds of future massive clusters. Watching these seeds grow through follow-up observations reveals how clusters assemble. The earliest protoclusters challenge formation theories. Dark matter simulations predict that only rare density peaks should collapse into bound structures so early. Finding multiple protoclusters at very high redshifts suggests either that rare peaks were sampled by chance or that structure formed faster than simulations predict. This connects to the same fast-track galaxy formation mystery affecting individual galaxies. Filaments connecting to clusters show organization into specific patterns. Typically, 2 to 4 major filaments feed each cluster. These filaments approach from different directions, creating a three-dimensional structure difficult to visualize from two-dimensional images. Mapping this structure requires spectroscopic redshifts for galaxies along each filament, building a three-dimensional picture of matter flows. Matter flowing along filaments toward clusters carries angular momentum. This angular momentum affects cluster properties by creating rotation and asymmetries. Some clusters show evidence of spinning slowly. Others exhibit lopsided distributions where one side contains more galaxies than the other. These asymmetries trace the directions from which material recently accreted. The intersection points where filaments meet create the universe's densest regions outside black holes and neutron stars. Here, dark matter concentrations reach values thousands of times higher than average cosmic density. These extreme environments test cosmological predictions. The densest peaks should collapse earliest and grow fastest. Observations generally confirm this pattern, with the most massive clusters associated with the highest density peaks in the early universe. But observations also reveal a puzzling abundance that standard models struggle to explain. Even after removing black hole contamination, the early universe contains twice as many massive galaxies as it should. Researchers carefully separated little red dots and other black hole-dominated objects from pure galaxy samples. They used spectroscopy to identify which light came from stars versus accreting black holes. They excluded any object where black holes contributed more than 20% of total brightness. The remaining sample contained only galaxies where starlight dominated. These cleaned galaxy samples still presented a problem. When astronomers counted how many galaxies exceeded 10 billion solar masses at different cosmic epochs, they found double the number predicted by lambda CDM simulations. At redshift 4, corresponding to when the universe was 1.6 billion years old, simulations predicted roughly 50 massive galaxies per cubic gigaparsec. Observations found 100. The discrepancy persists across multiple cosmic epochs. At redshift 6, 800 million years after the Big Bang, simulations predicted 5 massive galaxies per cubic gigaparsec. Observations revealed 10. At redshift 8, 600 million years after the Big Bang, simulations predicted 1 massive galaxy per cubic gigaparsec. Observations showed 2 to 3. The factor of 2 excess remains consistent across time. This consistency suggests systematic differences between simulated and real universe evolution rather than random fluctuations. If observations exceeded predictions by random amounts at different epochs, that would indicate measurement uncertainties or selection effects. A steady factor of 2 excess across billions of years points to missing physics in simulations. What could cause this discrepancy? Galaxy formation simulations include numerous physical processes. Dark matter gravitates and clusters. Gas falls into dark matter halos. The gas cools and forms stars. Stars produce energy through fusion. They explode as supernovae when massive enough. Supernova energy heats surrounding gas. This feedback regulates further star formation. Simulations model all these processes using equations derived from fundamental physics. The equations contain free parameters that cannot be calculated from first principles. Star formation efficiency is one such parameter. What fraction of cold gas converts to stars per unit time? Observations of nearby galaxies suggest roughly 1 to 10% efficiency. Simulations adopt values in this range. Increasing efficiency would produce more massive galaxies, but simply dialing up star formation efficiency creates other problems. Too efficient star formation depletes gas reservoirs quickly, leaving no fuel for ongoing star formation. Galaxies would form their stars in brief bursts, then go quiescent. Observations show early galaxies maintained star formation over extended periods, requiring sustained gas supplies. Reconciling high efficiency with sustained star formation proves difficult. Supernova feedback represents another uncertain parameter. How much energy do supernovae inject into surrounding gas? How effectively does this energy heat gas and prevent cooling? Strong feedback suppresses star formation by keeping gas too hot to collapse. Weak feedback allows more star formation. Simulations tune feedback strength to match observed galaxy populations in the nearby universe. Perhaps feedback operated differently in the early universe. Lower metallicity gas might have been harder to heat because it radiated energy less efficiently. With weaker feedback, more gas could cool and form stars despite supernova explosions. This would increase galaxy masses without requiring implausibly high star formation efficiencies. Dark matter halo assembly rates matter as well. If halos formed faster than simulations predict, they would attract gas more rapidly and enable quicker galaxy growth. Faster halo assembly might result from dark matter properties differing slightly from cold dark matter assumptions. Warm dark matter or self-interacting dark matter could alter assembly timelines. However, these alternatives struggle to match cosmic microwave background and large-scale structure observations. Another possibility involves gas accretion mechanisms. Simulations assume gas falls into halos gradually along filaments. What if gas arrived in more massive clumps or at higher rates? Direct observational evidence for gas accretion in the early universe remains limited. We see the results as galaxies, but tracking the actual gas flows proves challenging. The factor of 2 problem sits at an uncomfortable boundary. It is too large to dismiss as measurement uncertainty or simulation noise. Both observations and simulations have matured to the point where factor of 2 errors seem unlikely, yet the discrepancy is too small to break lambda CDM entirely. The standard model gets the approximate number of galaxies correct. It just misses by a consistent factor across cosmic time. Some researchers argue this validates lambda CDM. Getting within a factor of 2 represents remarkable success given the complexity of galaxy formation. Others view the persistent excess as a smoking gun, indicating missing physics. The debate continues as more data accumulates and simulations improve. What remains clear is that galaxies formed more massive and more numerous in the early universe than our best models anticipated. Something about early cosmic conditions favored efficient galaxy assembly. Modern galaxies waste most of their gas without forming stars. The Milky Way contains roughly 10 billion solar masses of cold molecular gas. This gas could form stars if it condensed sufficiently under gravity. Yet, the galaxy creates only 1 to 2 solar masses of new stars each year. At this rate, the current gas supply would last 5 to 10 billion years. Most gas never becomes stars. Stellar winds, supernova explosions, and radiation pressure from young stars heat the gas and disperse it before star formation completes. This inefficiency appears universal in present-day galaxies. Observations across hundreds of nearby galaxies show star formation efficiencies ranging from 1 to 10%. Only a small fraction of available gas converts to stars per dynamical time. The rest remains gaseous or gets ejected from galaxies entirely. Early universe galaxies might have operated under different rules. Several factors could have enhanced their star formation efficiency dramatically. First, the universe was denser overall. At redshift 6, all distances were 7 times smaller than today. This increased average cosmic density by a factor of 343. Denser environments mean stronger gravity relative to pressure support. Within galaxy dark matter halos, this higher density translated to deeper gravitational potential wells. Gas falling into these wells accelerated to higher velocities. When fast-moving gas clouds collided, The collisions generated stronger shocks. Shocks compress gas efficiently, triggering rapid cooling and star formation. The more violent conditions in early galaxies might have overwhelmed feedback mechanisms that suppress star formation today. Second, galaxy mergers occurred more frequently in the early universe. When galaxies collide, their gas clouds collide too. The collision compresses gas to high densities where star formation becomes inevitable. Merger-driven starbursts can form stars at rates hundreds of times higher than quiescent star formation. If early galaxies experienced constant mergers, they would maintain high star formation rates continuously. Third, gas cooling might have operated more efficiently despite lower metallicities. Metal-poor gas cannot cool as easily through metal line radiation. However, high gas densities compensate for low cooling efficiency. Dense gas cools through other processes like molecular hydrogen collisional excitation. In sufficiently dense environments, even primordial composition gas can cool rapidly to star-forming temperatures. Fourth, feedback might have been less effective at preventing star formation. Supernova explosions inject energy into surrounding gas, heating it and creating outflows that remove material from galaxies. In low-mass galaxies, these outflows easily escape because gravitational binding is weak. Gas blown out of small galaxies does not return. Star formation halts. Early massive galaxies sat in deeper gravitational wells than modern low-mass galaxies. Their escape velocities exceeded several hundred kilometers per second. Supernova-driven outflows struggle to reach such high velocities. Most gas heated by supernovae might have remained gravitationally bound, falling back onto the galaxy and forming additional stars. The feedback loop that regulates modern star formation may have failed in early massive systems. Observations support higher star formation efficiencies in distant galaxies. Measurements of gas masses and star formation rates in high redshift galaxies show they convert gas to stars several times faster than local galaxies. The depletion timescale, meaning how long current gas supplies last at current star formation rates, ranges from 100 million to 1 billion years for distant galaxies. This compares to several billion years for nearby galaxies. However, measuring gas masses in distant galaxies remains challenging. Most techniques rely on detecting emission from carbon monoxide molecules or dust continuum radiation. Both methods require assumptions about gas-to-tracer ratios that might not apply universally. If these assumptions fail, gas mass estimates could be systematically wrong, making efficiency calculations unreliable. Despite uncertainties, multiple independent lines of evidence point toward enhanced star formation efficiency in the early universe. Galaxies formed more stars per unit gas mass. They achieved higher stellar masses in shorter times. They depleted gas reservoirs faster. All these observations indicate physical conditions favoring efficient star formation. Understanding what created these favorable conditions requires detailed modeling of early galaxy environments. Simulations must capture gas dynamics, cooling processes, star formation, and feedback simultaneously across vast dynamic ranges. The physics operates on scales from individual star-forming clouds, measuring light-years across to entire galaxies spanning hundreds of thousands of light-years. Current simulations approximate small-scale physics using subgrid models. These models parameterize processes that occur below simulation resolution. The parameters get tuned to match observations of local galaxies. If early galaxies obeyed different physical relationships, these tuned parameters become incorrect. Simulations would underpredict star formation efficiency and produce too few massive galaxies, exactly the discrepancy observed. Solving this requires either better simulations with higher resolution capturing small-scale physics directly, or new observations constraining early galaxy gas properties more precisely. Both efforts are underway. Next-generation simulations run on the world's largest supercomputers. Next-generation observations use Webb to measure gas content in dozens of early galaxies. The early universe provided natural advantages for building massive galaxies quickly through efficient star formation. Density worked in favor of gravity. Frequent mergers compressed gas effectively. Feedback struggled to prevent cooling and collapse. These advantages enabled the rapid assembly that observations now reveal. But rapid star formation was not the only accelerant driving early galaxy growth. Gravity grows stronger as the universe ages, but it started with an advantage that later eras lost. When the universe was 1 billion years old, everything sat 7 times closer together than today. Space has expanded 7-fold since that epoch. This expansion dilutes matter density. The density at redshift 6 was 343 times higher than present cosmic density. 343 comes from 7 cubed, because density scales as the cube of distance. Higher density directly strengthens gravitational effects. Gravity depends on mass divided by distance squared. In a denser universe, masses sit closer together. Closer proximity increases gravitational force between objects. This affects how gas behaves within galaxies. Gas clouds that might resist collapse in the modern universe collapsed readily in the dense early universe. Consider a molecular cloud with 1,000 solar masses of gas spread across 10 light-years. In the modern universe, this cloud has a characteristic density and gravitational binding energy. Whether it collapses to form stars depends on whether gravity overwhelms internal pressure support. Thermal pressure, turbulent motions, and magnetic fields all resist gravitational collapse. The cloud collapses only if gravity exceeds the sum of these opposing forces. Place the same cloud in the early universe. External pressure from surrounding gas increases by a factor of 343. This external pressure compresses the cloud, increasing its internal density. Higher internal density strengthens self-gravity. The cloud becomes more prone to collapse. Star formation initiates more easily and proceeds more rapidly. The same logic applies at galaxy scales. Early galaxies existed in environments with higher ambient gas densities. Gas falling into galaxy dark matter halos arrived pre-compressed compared to modern infall. It needed less additional compression to reach star-forming densities. Star formation could begin immediately upon infall, rather than requiring extended cooling times. Galactic dynamics also benefited from higher densities. Galaxy rotation curves show how fast stars and gas orbit at different radii. These curves trace the underlying gravitational potential. In denser early universe environments, potential wells reached greater depths for given dark matter halo masses. Deeper potentials bound material more tightly. This tighter binding prevented gas from escaping easily when supernovae exploded. Supernova explosions inject roughly 1 to 10 solar masses worth of kinetic energy per event. This energy heats surrounding gas and can drive outflows. If heated gas reaches escape velocity, it leaves the galaxy permanently. Star formation halts when all gas escapes. Escape velocity scales with the square root of mass divided by radius. Early galaxies with higher densities had smaller radii for given masses. Smaller radii mean higher escape velocities. Gas had to reach higher speeds to escape. Most supernova-heated gas failed to reach escape velocity and fell back onto the galaxy. Feedback became less effective at regulating star formation. The density advantage extended to dark matter as well. Dark matter halos formed through gravitational collapse of dark matter over densities. Higher overall cosmic density meant all overdensities were denser in absolute terms. Dense overdensities collapse faster under their own gravity. This accelerated halo formation timelines. Faster halo formation meant galaxies could begin assembling earlier. A halo that takes 1 billion years to form at redshift 0 might form in only 500 million years at redshift 6. This shortened timeline allowed more massive halos to exist at early times. More massive halos attract more gas and form more massive galaxies. Halo mergers also occurred more frequently in denser environments. When halos sit closer together, gravitational interactions happen more often. Mergers bring galaxies together, combining their stellar populations and gas supplies. Merger rates at redshift 6 exceeded modern rates by factors of 10 to 100. This merger activity rapidly assembled mass into large systems. Cosmic expansion worked against these advantages by continuously diluting densities. As the universe expanded, densities dropped, gravitational effects weakened, star formation became less efficient. Halo assembly slowed. The transition from early rapid assembly to later gradual growth reflected decreasing cosmic density over time. Modern galaxy formation occurs in a relatively gentle environment. Densities are low, feedback easily regulates star formation. Halos assemble slowly through smooth accretion rather than violent mergers. The density advantage of the early universe has vanished. Contemporary galaxies grow through fundamentally different processes than their early counterparts. This difference explains why early galaxies assembled so quickly. They enjoyed physical advantages unavailable to later generations. High densities, strong gravity, frequent mergers, and ineffective feedback combined to create ideal conditions for rapid, massive galaxy formation. Once cosmic expansion diluted densities below critical thresholds, galaxy formation entered a new regime governed by different physics. Yet, something else accelerated early cosmic evolution even beyond density advantages. Supermassive black holes appeared impossibly early and grew impossibly fast. Webb detected a quasar, shining when the universe was just 340 million years old. This quasar, designated CERS 1019, contains a black hole massing roughly 9 million times our stellar mass. It sits near the center of a galaxy actively forming stars. The galaxy's light redshifted dramatically, indicating extreme distance. Spectroscopy confirmed the redshift exceeded 16, placing it in the universe's first few 100 million years. 9 million solar masses seems modest compared to billion solar mass black holes found in later cosmic epochs. However, forming even a 9 million solar mass black hole in just 340 million years presents severe challenges. Black hole growth occurs through accretion. Material spiraling into the black hole releases gravitational energy as radiation. This radiation exerts outward pressure on additional infalling material. When radiation pressure balances gravitational pull, accretion reaches the Eddington limit. This limit depends on black hole mass. More massive black holes can accrete faster while remaining below the Eddington rate. But the growth still requires time. A stellar mass black hole of 10 solar masses accreting at the Eddington limit doubles its mass every 10 million years. Starting from 10 solar masses and doubling 20 times yields 10 million solar masses. 20 doublings require 200 million years at Eddington limited accretion. This barely fits into the 340 million year timeline. It requires the black hole to begin forming almost immediately after the Big Bang with no delays. It also requires continuous Eddington limited accretion with no interruptions or slow periods. Both assumptions seem unrealistic. Black holes likely did not form at the Big Bang. The first stars had to form, live, and die before leaving black hole remnants. This process takes at least a few million years for the most massive stars. More likely, it took tens to hundreds of millions of years for the first stellar mass black holes to appear. Starting later leaves insufficient time to reach 9 million solar masses through Eddington limited growth. Moreover, continuous accretion rarely occurs in nature. Accretion requires available fuel. Gas must flow toward the black hole consistently. In galaxies, gas supplies fluctuate based on star formation activity, mergers, and environmental factors. Periods of rapid accretion alternate with quiet periods. Accounting for these variations extends growth timelines significantly. The solution might involve super-Eddington accretion or massive seed black holes. Super-Eddington accretion happens when gas flows into the black hole faster than radiation can push it away. This requires specific geometries where radiation escapes preferentially in certain directions, while gas continues flowing in from other directions. Some simulations show early black holes achieved super-Eddington growth under dense gas conditions. Alternatively, black holes might have formed with initial masses far exceeding stellar remnants. Direct collapse of primordial gas clouds could create black holes massing hundreds of thousands of solar masses without forming stars first. These massive seeds could reach millions of solar masses quickly through even modest accretion. Direct collapse requires special conditions. The gas cloud must remain hot enough to resist fragmentation into stars. Temperatures need to exceed several thousand Kelvin throughout the collapse. Normally, cooling processes drop temperatures below this threshold, allowing fragmentation. Preventing cooling requires either heating from nearby radiation sources or preventing molecular hydrogen formation, since molecular hydrogen cools gas efficiently. Some regions in the early universe might have met these conditions. Intense ultraviolet radiation from nearby galaxies could dissociate molecular hydrogen and keep gas warm. These rare environments could host direct collapse black hole formation. However, whether they occurred frequently enough to explain all early supermassive black holes remains uncertain. CEERS 1019 is not unique. Webb has found multiple quasars at redshifts exceeding 10. Each one pushes black hole formation theories. The earliest confirmed quasar exists at redshift 16.6, just 200 million years after the Big Bang. Its black hole masses roughly 1.6 million solar masses. Even this relatively modest mass strains formation scenarios, when the timeline compresses to 200 million years. The abundance of these early quasars matters as much as their existence. If only one or two existed, they could represent extraordinarily rare objects formed under exceptional circumstances. Instead, dozens have been discovered. The number keeps growing as surveys expand. This abundance suggests black hole formation and growth proceeded efficiently in the early universe, not as rare accidents, but as common occurrences. Understanding how black holes grew so massive so quickly represents one of modern astrophysics' major challenges. The physics of accretion is well established. The Eddington limit follows directly from balancing radiation pressure against gravity. Yet observations demand black holes exceeded these limits regularly or started from unexplained massive seeds. Either the physics operates differently than thought, or formation mechanisms exist that current theories have not included. Both possibilities require new ideas about the early universe. Both challenge conventional wisdom about structure formation and galaxy evolution. The black holes did more than just grow. They profoundly affected their host galaxies through energetic feedback. When black holes consume matter, they release energy equivalent to 1% of the infalling mass converted directly to radiation. This conversion efficiency vastly exceeds nuclear fusion, which converts about 0.7% of mass to energy. Accretion onto black holes ranks as the most efficient energy generation mechanism in the universe aside from matter-antimatter annihilation. For a black hole accreting 10 solar masses per year, the released energy reaches 40 times the luminosity of the entire Milky Way galaxy. This tremendous energy does not disappear. It heats surrounding gas, ionizes atoms, and drives powerful outflows. These winds sweep through galaxies at velocities exceeding 1,000 kilometers per second. At such speeds, gas crosses a galaxy, measuring 100,000 light-years in about 100 million years. The winds reach every corner of the galaxy, carrying energy far from the central black hole. Webb detected these winds in early universe galaxies through spectroscopic signatures. Emission lines from ionized gas show characteristic broadening and shifting. Broadening indicates velocity dispersion as different gas parcels move at different speeds. Shifting shows bulk motion as gas flows outward from the black hole. The magnitude of these effects reveals wind velocities and mass outflow rates. Some early quasars drive winds carrying hundreds of solar masses per year. This exceeds their accretion rates substantially. For every unit of mass accreted onto the black hole, several units get expelled in winds. The expelled mass comes from the broader galaxy gas reservoir, rather than just material already spiraling toward the black hole. Winds couple to ambient galaxy gas, sweeping it up and carrying it away. These outflows create bubbles of hot, shocked gas expanding through galaxies. As the wind plows through surrounding material, it creates a shock front. Gas crossing the shock heats to millions of degrees and emits X-rays. X-ray observations reveal these bubbles, extending across tens of thousands of light years. They contain enormous energy, sometimes exceeding the total kinetic energy of all stars in the host galaxy. The energy injection affects star formation profoundly. Cold molecular gas must reach temperatures below 100 Kelvin to collapse and form stars. Wind-heated gas reaches temperatures of millions of Kelvin. Cooling from such high temperatures back to star-forming conditions takes billions of years. During this time, star formation halts. The galaxy becomes quiescent despite containing substantial gas mass. This process, called AGN feedback, where AGN means active galactic nucleus, represents a crucial mechanism regulating galaxy growth. Without feedback, galaxies would convert all their gas into stars quickly. They would become far more massive and star-filled than observed. Feedback prevents this runaway star formation by removing or heating gas supplies. Observations show correlations between black hole mass and host galaxy properties. More massive black holes sit in more massive galaxies with larger stellar velocity dispersions. This correlation suggests coevolution. Black holes and galaxies apparently regulated each other's growth throughout cosmic history. When black holes grew rapidly through accretion, their feedback suppressed galaxy star formation. When black holes shut off and stopped accreting, galaxies could resume star formation. Early universe observations reveal this feedback operating already. Galaxies hosting active quasars show suppressed star formation rates despite abundant gas. Their gas has been heated or removed by black hole winds. Nearby galaxies without active black holes show vigorous star formation. The presence or absence of black hole activity determines whether galaxies grow or go dormant. Wind velocities in early galaxies exceed escape velocities in many cases. Gas accelerated beyond escape velocity leaves the galaxy permanently unless cosmic expansion turns it around and it falls back billions of years later. This permanent removal represents a loss of baryonic mass from galaxies. Dark matter remains bound by gravity, but ordinary matter escapes carried by winds. The lost baryons end up in the circumgalactic and intergalactic media. These reservoirs surrounding galaxies contain gas expelled by feedback processes. Observations indicate that more baryonic mass exists in these diffuse reservoirs than in galaxies themselves. Most ordinary matter never formed stars, and never will, because feedback expelled it from galaxies. Black hole winds reach such high velocities through radiation pressure and thermal driving. Photons emitted by the accretion disk carry momentum. When these photons scatter off electrons in surrounding gas, they transfer momentum and accelerate the gas outward. This radiative acceleration can reach very high velocities, limited only by the speed of light. Thermal driving adds to radiative acceleration. Gas heated to 10 million Kelvin has thermal velocities around 1,000 kilometers per second. This hot gas expands rapidly from overpressure. The combination of thermal and radiative driving creates the observed wind velocities. Some winds show evidence of being collimated into jets rather than spherical outflows. Jets form when magnetic fields near the black hole channel gas along the rotation axis. These jets can reach velocities approaching light speed and extend for millions of light years beyond their host galaxies. They carry enormous energy and momentum into intergalactic space. The winds reshaped the early universe by redistributing gas and energy across vast volumes. They enriched the intergalactic medium with heavy elements formed in stars. They heated gas that would otherwise cool and form additional galaxies. They coupled black hole growth to galaxy evolution fundamentally. This coupling created the observed relationships between black holes and galaxies that persist to the present day. Black holes prevent galaxies from forming stars despite abundant gas supplies. This seems paradoxical. Galaxies contain billions of solar masses of cold molecular hydrogen. This gas sits in the gravitational potential well of the galaxy. It should collapse and form stars. Yet observations show many massive galaxies with large gas reservoirs, forming very few new stars. Their star formation rates drop below 1 solar mass per year, despite having gas supplies that could sustain hundreds of solar masses per year. The explanation lies in gas heating. For gas to collapse and form stars, it must cool below roughly 100 Kelvin. At these temperatures, thermal pressure becomes weak relative to gravitational pull. Gas clouds can contract under gravity. As they contract, they fragment into smaller clumps. These clumps continue collapsing until densities reach levels where nuclear fusion ignites. Stars are born. Heating gas above 100 Kelvin increases thermal pressure. Hot gas resists gravitational compression. It expands rather than contracting. Even if gas cools somewhat, maintaining temperatures above a few thousand Kelvin prevents star formation indefinitely. The thermal energy overwhelms gravity for typical molecular cloud masses and sizes. Black hole activity provides the necessary heating. Radiation from the accretion disk bathes the galaxy in energetic photons. These photons ionize hydrogen atoms, splitting them into protons and electrons. Ionization requires energy. The energy comes from the photon field. When ionized gas recombines, some energy radiates away, but much converts to thermal motion. The gas heats up. Energetic photons also create photoelectric heating. When ultraviolet photons strike dust grains, they eject electrons. These fast-moving electrons collide with surrounding gas atoms, transferring kinetic energy. The gas temperature rises further. Photoelectric heating from bright quasars can maintain gas temperatures around 10,000 Kelvin throughout a galaxy. At 10,000 Kelvin, gas cannot form stars. The thermal pressure exceeds gravitational collapse thresholds by orders of magnitude. Star formation shuts down completely, despite abundant fuel. This explains why galaxies hosting bright, active galactic nuclei show suppressed star formation. The black hole heats gas faster than it can cool. Winds from black holes provide mechanical heating as well. High-velocity winds carry kinetic energy. When these winds collide with stationary galaxy gas, the collision creates shocks. Shocks heat gas to millions of Kelvin. This extreme heating far exceeds what radiative processes alone achieve. Once gas reaches such temperatures, cooling timescales extend to billions of years. The combination of radiative and mechanical heating creates a feedback loop. Black holes accrete gas and grow. Growing black holes emit more radiation and drive stronger winds. Stronger winds heat more gas and prevent star formation. Without star formation, less gas gets incorporated into stars. More gas remains available for the black hole to accrete eventually. The cycle continues until the black hole has grown massive enough or expelled enough gas that accretion rates drop. Observations reveal this process in action. Galaxies in transition from star-forming to quiescent show signs of recent black hole activity. Their spectra indicate ionized gas heated by active galactic nuclei. Their star formation rates decline rapidly over timescales of 100 million to 1 billion years. Eventually, they reach quiescent states with minimal star formation despite retaining gas. The timing of this quenching correlates with black hole mass. More massive black holes quench their host galaxies earlier in cosmic history. Lower mass black holes allow star formation to continue longer. This creates a mass-dependent evolutionary sequence. The most massive galaxies formed their stars earliest and shut down first. Lower mass galaxies continued forming stars longer and remain somewhat active today. This mass-dependent quenching explains observed galaxy color distributions. Massive galaxies appear predominantly red, indicating old stellar populations and little recent star formation. Lower mass galaxies span blue to red colors, showing a range of star formation histories. The smallest galaxies remain blue, still actively forming stars because their low-mass black holes provide insufficient feedback to quench star formation. The relationship between black hole mass and quenching creates the observed correlation between black hole mass and galaxy stellar velocity dispersion. Velocity dispersion traces total galaxy mass, including dark matter. More massive galaxies have higher velocity dispersions. They also host more massive black holes. The correlation arises because black hole growth and galaxy quenching couple through feedback. Without black hole feedback, simulations produce too many massive galaxies with too many stars. Observed galaxy stellar mass functions show a sharp decline at the high mass end. Few galaxies exceed 100 billion solar masses in stars. Simulations without feedback produce many more such massive galaxies. Including feedback suppresses this overgrowth and reproduces observed mass functions. Star formation suppression by black holes thus plays a crucial role in galaxy evolution. It explains why massive galaxies stop forming stars despite retaining gas. It creates the observed relationships between black hole and galaxy properties. It regulates the overall efficiency of star formation across the universe. This regulatory mechanism emerged early in cosmic history, shaping galaxy evolution from the first billion years onward. The evidence appears throughout Webb's observations of distant galaxies. The same feedback processes operating today were already active when the universe was less than 10% its current age. These discoveries place unprecedented strain on cosmology's standard framework. Lambda CDM cosmology describes a universe dominated by dark energy and cold dark matter. Lambda represents the cosmological constant, a form of dark energy that causes accelerating cosmic expansion. CDM stands for cold dark matter, meaning dark matter particles moving slowly compared to light speed. Together, these components make up 95% of the universe's total mass energy. Ordinary matter contributes only 5%. Despite being the minority component, ordinary matter produces all visible structure: stars, galaxies, planets, and life. Lambda CDM succeeds spectacularly at explaining large-scale cosmic structure. It predicts the pattern of temperature fluctuations in the cosmic microwave background with extraordinary accuracy. It explains why galaxies cluster in specific ways across billions of light years. It accounts for the abundance of light elements created in the Big Bang. It describes how gravitational lensing distorts images of distant objects. Dozens of independent observations confirm Lambda CDM predictions. Yet Webb's discoveries challenge this successful model at multiple points. The expansion rate discrepancy cannot be resolved within standard Lambda CDM. Observations consistently yield 74 km per second per megaparsec. Cosmic microwave background predictions yield 67. Modifying Lambda CDM to accommodate higher expansion rates risks breaking other successful predictions. Early massive galaxies present another challenge. Lambda CDM predicts hierarchical structure formation, where small objects merge into larger ones gradually. This process requires billions of years to build massive galaxies. Webb finds massive galaxies already assembled within the universe's first billion years. The timeline seems too short for hierarchical assembly to complete. Supermassive black holes appearing within a few 100 million years after the Big Bang strain formation scenarios. Standard black hole growth through accretion cannot reach observed masses in available time. Either accretion occurred faster than the Eddington limit allows, or black holes started from unexplained massive seeds. Both options require physics beyond Lambda CDM. The abundance of massive galaxies at high redshift exceeds predictions by factors of 2. This discrepancy persists after careful accounting for observational effects and black hole contamination. Something about early galaxy formation operated more efficiently than simulations capture. The missing ingredient remains unidentified. These tensions create two possible responses. First, Lambda CDM might need modifications to its underlying assumptions. Perhaps dark energy's strength changed over cosmic time rather than remaining constant. Perhaps dark matter interacts through forces beyond gravity. Perhaps initial conditions from the cosmic microwave background era differ from what we infer. Second, lambda CDM might be fundamentally correct while astrophysics needs refinement. Perhaps star formation, black hole growth, and feedback operate differently than current models assume. Perhaps simulations miss important processes that become crucial in the early universe. Perhaps our understanding of how gas cools, collapses, and forms stars contains systematic errors. Distinguishing between these possibilities requires more observations and better simulations. Webb provides the observations. Next-generation supercomputer simulations can test different physics prescriptions. Progress happens through iteration between theory and observation. Some physicists propose exotic solutions. Early dark energy would inject extra energy into the universe shortly after the Big Bang, accelerating expansion beyond predictions from cosmic microwave background data alone. This could resolve the Hubble tension by increasing predicted present-day expansion rates. However, early dark energy affects other observables as well. It must increase expansion rates without disrupting structure formation or cosmic microwave background patterns too severely. Modified gravity theories offer another path. What if Einstein's general relativity requires corrections on cosmological scales? Modified gravity could alter expansion rates and structure formation simultaneously. However, general relativity has passed every experimental test conducted in laboratories and in the solar system. Modifying it to fix cosmological tensions while preserving local successes proves extremely difficult. Self-interacting dark matter allows dark matter particles to scatter off each other through forces beyond gravity. This could accelerate structure formation by allowing dark matter to lose energy and collapse faster. It might explain early massive galaxies. Yet self-interactions must remain weak enough to preserve cosmic microwave background predictions and large-scale structure observations. The allowed parameter space is narrow. The most conservative interpretation says lambda CDM requires minor adjustments rather than wholesale replacement. The model captures reality approximately. Fine-tuning parameters within uncertainties could reconcile most tensions. Star formation efficiency, feedback strength, initial mass function variations. These astrophysical details might suffice to explain observations without invoking new fundamental physics. This conservative view faces the problem of multiple independent tensions, all pointing in similar directions. The expansion rate disagreement stands alone as a cosmological tension. Early galaxy abundance represents an astrophysical tension. Early black hole growth creates another astrophysical challenge. If these tensions were unrelated, conservative adjustments to individual pieces might work. But if they connect through underlying physics, minor adjustments seem insufficient. The debate continues as evidence accumulates. Every new Webb observation tests lambda CDM from different angles. So far, the model bends under strain but has not broken. Whether it will break or adapt successfully remains the defining question in cosmology today. Part of the strain comes from our incomplete understanding of the universe's primary component, dark energy. 68% of the universe consists of something we cannot see, touch, or directly detect. Dark energy reveals itself only through its gravitational effects on cosmic expansion. Einstein's equations relate space-time curvature to energy content. Observations show the universe expands at an accelerating rate. This acceleration requires a component with negative pressure, a repulsive gravitational effect. Dark energy provides this pressure. The simplest model treats dark energy as the cosmological constant. Einstein originally introduced this constant in 1917 to create a static universe model. He later called it his biggest blunder when Hubble discovered cosmic expansion. The static universe was wrong, yet the cosmological constant itself appears to be real, driving accelerating expansion. A cosmological constant represents vacuum energy. the energy of empty space itself. Quantum field theory predicts that vacuum contains fluctuating quantum fields. These fluctuations contribute energy density even in empty space. The problem is magnitude. Quantum field theory predicts vacuum energy densities many orders of magnitude larger than observed. This discrepancy represents one of physics's most severe fine-tuning problems. The observed dark energy density equals roughly 0.7 times 10 to the minus 26 kilograms per cubic meter. This tiny value produces just enough repulsive gravity to accelerate expansion at observed rates. Yet naive quantum field theory calculations predict densities 120 orders of magnitude larger. If vacuum energy reached predicted levels, the universe would have exploded instantly, allowing no structure to form. Why does vacuum energy nearly vanish relative to predictions? No accepted explanation exists. Some physicists invoke anthropic reasoning. In a multiverse containing regions with different vacuum energies, only regions with appropriately small values allow galaxy and star formation. We observe a small value because large values would have prevented our existence. This reasoning satisfies few physicists. Alternative dark energy models allow the energy density or pressure to change over time. These dynamical dark energy models involve scalar fields permeating space. The field value determines energy density. As the field evolves, energy density changes. Different potentials governing field evolution produce different expansion histories. Quintessence models assume a slowly rolling scalar field. The field gradually changes value over cosmic time. This produces dark energy density that varies smoothly rather than remaining strictly constant. Phantom energy models allow even stranger behavior, where dark energy density increases with time. This leads to eventual runaway expansion, tearing apart all structure in a big rip. Distinguishing between these models requires precise measurements of expansion history across cosmic time. Type Ia supernovae serve as standard candles, allowing distance measurements at different redshifts. Comparing distances to redshifts reveals expansion rates at different epochs. If dark energy remains constant, the relationship follows specific predictions. Deviations indicate evolving dark energy. Current observations slightly favor a constant cosmological constant over varying alternatives. The data allow some variation but not dramatic changes. More precise measurements could rule out constancy in favor of slow evolution or confirm constancy within tighter bounds. Dark energy's equation of state parameter W encodes this information. The parameter relates pressure to energy density. For a cosmological constant, W equals -1 exactly. For dynamical dark energy, W differs from -1 and potentially changes over time. Measurements constrain W to within roughly 10% of -1. Whether it differs from -1 significantly remains uncertain. The Hubble tension connects to dark energy properties. If dark energy behaved differently in the early universe, it would affect expansion rates then versus now. Perhaps dark energy was weaker or absent at early times, only activating recently. This scenario could alter predictions from cosmic microwave background data to match present-day measurements. Another mystery involves dark energy's relationship to cosmic structure. Does dark energy cluster gravitationally like matter, or does it remain perfectly smooth across space? Clustering dark energy could affect structure formation on large scales. Current observations suggest dark energy distributes uniformly, but uncertainties remain. Dark energy also determines the universe's ultimate fate. If dark energy represents a true cosmological constant, expansion will accelerate forever. Galaxies will separate increasingly rapidly. Eventually, only gravitationally bound structures like our local galaxy cluster will remain visible. Everything else will recede beyond our cosmic horizon, unreachable even at light speed. If dark energy varies with time, other fates become possible. Decreasing dark energy could lead to eventual recollapse in a big crunch. Increasing dark energy could accelerate expansion so violently that it tears apart galaxies, stars, and eventually atoms in a big rip. The fate of the universe depends on dark energy's nature. Understanding dark energy represents physics' greatest observational challenge. We can measure its effects, but cannot explain its origin. No fundamental theory predicts the observed value from first principles. It might emerge from quantum gravity or string theory, but these frameworks remain incomplete. Some proposals suggest dark energy is not a fundamental component, but rather an effect of modified gravity. Perhaps general relativity requires corrections at cosmological scales. These corrections could mimic dark energy without requiring a new energy component. Testing such ideas requires measurements at the precision frontier. Dark energy's mysteries deepen when considering possible early universe variations.